Welcome you all to this course on diffraction and imaging. So, what did we essentially start with is if we have a sample, okay, and if we beam of any radiation, okay, and wave you consider the electromagnetic wave is falling onto the sample, okay. A sphere with a sample at the center, if we take it and keep a detector, okay, and if we move the detector around on all points in the sphere, okay, at some points we get high intensity, at some point there is reduction in intensity. When such a phenomena occurs, then we say that a diffraction is taking place in that sample, right. That is essentially what we have seen. Okay. So, the next that question which comes is that if the beam can be considered as a plane wave, okay, if you consider it as a plane wave traveling in this direction k, okay, how do you define the wave vector of the wave, plane wave? The incident beam, it is represented as, it will be 1 by lambda, okay, and when we represent it as a vector, okay, it will have a direction also associated with it. So, this is essentially going to be the magnitude of k, because the wave we represent it as psi equals some constant a e to the power of 2 pi I k dot or kr, we can write it, okay. So, this k is what we call it as. So, if we fix a coordinate system and you assume that this is what, assume that this is k0, okay. Signal which comes out is also the same radiation without no change in wavelength, correct. Incident beam, that means that scattering is an elastic scattering which we are considering it. So, what will be the wave vector corresponding to that? That should also be corresponding to k, okay, suppose equals 1 by lambda, correct. So, how will you represent this when in a vectorial form? So, once you fix a coordinate and if you assume this to be k0, all other vectors, since the magnitude remains the same, okay, the end of the vector is going to lie on this sphere, and we can represent with respect to what is the angle which it submits with respect to, that is how we define. Once we have fixed the wavelength of the radiation, we know what the value of magnitude of k is going to be, okay. So, irrespective of whatever be the direction in which the scattering is taking place, okay, the magnitude of each of the scattered vector is always going to be 1 by lambda, okay. So, if you take a locus of all the vectors which are there with respect to the origin, okay, all these reciprocal lattice vectors, not reciprocal, all these scattered the beam vectors is going to lie on a sphere, on the surface of the sphere it will come, correct. So, this is what is the basis of a wall sphere construction. You understand that? Okay. That is, if this is the incident beam and this is the vector k and this is k dash is the scattered vector, okay, and since the magnitude remains the same for both of them, with respect to this point as the center, if you try to draw, okay, in this particular case it will be a circle, in 3 dimension it is going to be a sphere. That sphere we call it as the Wald sphere, okay. What is the relationship between this relationship between all the points? That means that the scattered vector will be lying on the surface of the sphere, correct. the primary beam is also lying on the primary beam vector is also lying on the surface of a sphere, and the scattered beam vector when it lies on the surface of the sphere, then the diffraction condition is satisfied. So, this will be the vector G which is going to be. How to draw a evolved sphere is that you choose any point as the origin in the evolved sphere. Okay. From that, suppose we have suppose we choose this as the point. From this point, you choose the direction we know in which the beam is coming, the k we know that. So, the vector k you try to measure from this point in this direction, the direction of the beam which is coming. Okay. And this point as the center, now you draw a sphere. Okay. So, if you draw as a sphere, then try to look for what all points are going to lie, reciprocal lattice points are lying on the surface of this sphere. All these points are the ones, okay, which will give rise to diffraction for the specific direction in which the beam is falling onto the sample. Okay. So, only those points will give rise to diffraction. Though reciprocal lattice has got lot of points are there on the reciprocal lattice. Okay. Now, the incident beam direction for a specific value of the wavelength of the incident radiation, okay, and for the particular direction in which the beam is entering, okay, what all the directions or what all the reciprocal lattice parts which will give rise to diffraction is defined. Okay. And from this construction, reciprocal evolved sphere construction, one can understand it. So, what have I done here, okay, is that if you look for an X-ray, no, wavelength of the radiation is almost of the same order as the lattice parameter, whereas in the case of electrons, if we take it, the wavelength of the radiation is 100 times smaller than that of the lattice parameter spacing. Okay. In fact, if we use k alpha of tungsten, then the wavelength of the k alpha of tungsten is 10 times smaller than that of the normally the lattice parameter spacing. Okay. So, what I have done it is with respect to origin in the reciprocal lattice of a crystal has been constructed. Okay. This is what the reciprocal lattice is taken at this point as the origin. Okay. This is the direction in which the beam is coming. So, I can know what the value of k is that. So, I can mark this point, correct. So, with this as the center, this is for wavelength equals 0.01. Okay. I have just drawn the, because this is also taken, reciprocal lattices are drawn with respect to some lattice parameter, okay, it is drawn to scale. You can draw the sphere and the sphere cuts here as a circle. Okay. Now, you can find out what all points, okay, reciprocal lattice points which are touching the surface of the sphere. Only for this particular beam direction, all of them will give rise to a diffraction spot, which in the last class I have shown you that for a particular beam direction, more than in one direction in which you will be getting the Bragg diffraction, correct. So, now when the radius of the sphere has become very large or the wavelength has become very small, now you can see that the points which are touching are essentially points almost lying on a plane itself, correct. And this is for the ratio of lattice parameter, okay, to the wavelength, okay, it is going to be 10. When it becomes 100, you can imagine where exactly it is going to be there. Then almost a reciprocal lattice plane is what is cutting the evolved sphere. So, all the spots which are there on those on that surface, will give rise to diffraction. And another point becomes obvious is that in such a case, here only very few spots are touching. So, the number of diffraction which you get for a particular beam direction is going to be small for X-ray diffraction, conventional X-ray diffraction with copper K alpha or molybdenum K alpha if you use it. Okay. And for electron beam, you can understand that the more number of spots will be coming, correct. But what is going to be the consequence of it is that the Bragg angle will become smaller and smaller. Okay. So, essentially the physical meaning of this evolved sphere is that using this evolved sphere construction, looking at the reciprocal lattice, we can immediately, if we can define what is the direction in which beam is falling, we can immediately tell that these are all the diffraction spots which will appear in the diffraction pattern for that particular orientation in which the incident beam is falling on the sample. Okay. Okay. This whatever we have done so far, the last slide is all with respect to a reciprocal space we have considered, correct. Okay. But when we do experiment, when we are collecting an information on diffraction pattern, it is done in a real distance, correct. That is what we do. That means that this is a sample, okay. This is the incident beam which is falling. I had just shown lattice plane which is inclined, okay. For this particular plane, it gives rise to a diffraction, and the screen is kept at some particular distance L, okay. Then you get at a particular point from the center, you will be getting the diffraction spot, correct. So, the relationships are this d divided by L will be tan 2 theta t 2 theta, and 2d sin theta will be lambda by d, okay. And when theta is small, we will get 2 theta equals d by L equals lambda by d. This gives rise to some relationship. The distance in reciprocal space multiplied by the distance in L space equals wavelength of the radiation times the distance at which the screen is kept from the sample. Okay. So, this distance in electron microscopy is normally called as the camera constant. L is called as a camera constant, camera length, and lambda L is called as a camera constant. Okay. This constant is the one which will tell us, okay, how much time this d is magnified. Otherwise, how do we define d star? D star equals 1 by d, correct, right. So, this d here equals lambda L into 1 by d, correct. So, this is the sort of a magnification factor which is used to define the distance in to measure the distance in actual diffraction pattern. I am just showing the sample, okay. You look at this, these are all the planes which is going to give rise to diffraction, correct. This is where we are measuring the screen at this particular distance, we are capturing this diffraction pattern. The reciprocal lattice is shown here, okay, with the origin at this point, okay, and this is what the evolved sphere is, okay. This is the way it looks like. If I tilt the sample, what will happen? Because this is related to a sample, the evolved sphere remains the same because it is fixed by the wavelength of the radiation, correct. What is going to happen is that the reciprocal lattice will tilt, correct. Now, when the reciprocal lattice has tilted, now you see that what all spots which are touching the surface of that sphere, those are all the only ones which are going to appear as diffraction pattern on the screen, correct. Now, from this you can understand that these two are related to each other, okay. One is tied with the other. Then from the same relationship, another interesting information comes, because this delta k equals g is the crux of the whole diffraction when we look at a vector. What essentially is that from this we can get the concept of Brillouin zone. What is the Brillouin zone concept which you have studied? Do you have an idea? Primitive lattice. Other than that, with respect to a distribution of electrons in a sample, then you have studied. No, free electron concept you have studied, no? Free electron concept, what it means?
particular atom as such, but
Yeah, but all these electrons, can they have any energy? If it is a free electron model, they can have an energy which is continuous energy can be there with the electrons. Okay, and the relationship is E equals k squared, it will come. So what we essentially try to plot is that energy versus k. If you try to plot it, this is with respect to some pi by a, and okay, all these things will come. Okay, essentially this is the way the distribution will be going, correct? What it happens when there is a potential, positive potential is associated, the periodic potential is there, or when we consider that it's essentially atoms are there with positive nucleus which has some potential associated with it, and only few, then some gaps come, right? So this is where some gaps will be coming in this energy which is coming, will come corresponding to these various values of k by a, it will come. Okay, this gap which is there, this boundary of these values of k which corresponds to that energy, this is called as the Brillouin-Zone boundary. What it means is that if I put an electron in that particular k direction with an energy which is there in the which is not corresponding to what is dictated by the which the electron can have in that sample, all those will be just thrown out. How will it be thrown out? They will be scattered back.
if the electron, if band gap means that there can't be an electron with that particular energy.
That in that energy level, if we try to put an electron with that energy, it cannot remain with that energy in that sample. That is what the band gap means. That is, electrons occupy some specific levels and some energy values are not permitted. Okay. So if we put any radiation with an energy which is different from this, suppose I try to push into that sample electron with an energy which is much different from that, either that electron has to lose energy by some collision with it, or it has to be reflected out of that sample, scattered out of that sample, if the full energy has to be there. The same is true for also. So the boundary at which this happens, that k values, this we call it as the Brillouin-Zone boundary. Essentially what happens is that if you look at this, this is k minus k0 equals g, okay. This we can write it in another form, k equals k0 plus g, also we can write it. If you take the dot product and all, finally what it will happen is that this sort of a relationship will come. G the whole square. Okay. This you can just work out. This is okay. See, this will turn out to be k squared. Okay. This will be k0 squared plus g squared. Okay. Plus 2 k0 dot g will come here in this picture. Okay. These values are the same, they will go. So g squared plus 2 k0 into g will come. From this sort of an expression will come. What does this expression essentially mean? This is nothing but k dot half g equals half g dot half g. This how we can look at it is that when a Bragg diffraction is taking place, okay, this is just a mathematical derivation. To try to make a sense out of it is that this is a reciprocal lattice vector from here to here, this is the incident beam direction, and this is the direction in which scattering is taking place. So the delta k has to be equal to g. So g means that this is one reciprocal lattice vector, this is another reciprocal lattice vector. Similarly here this is one and this is another one, right. So these vectors can be written as this way also. This is k dash, okay, and this direction is from here to here, this is that minus k, correct. And if you look at the mid plane of this, what does this half g means vector? Is from the origin half of this distance, correct? This is the vector. If you draw a plane perpendicular to this vector, okay, the scattering vectors touch that plane, correct? This is k and k dash are the scatter vectors, incident beam direction and the scattered beam direction. Both of them are touching this surface. Is it not? Is it clear?
K is not touching, only K dash is
All touch.
if you consider a plane and half of
See, vector you can draw anywhere. Okay. The vector is from the origin we normally define all the vectors, but if you see this from this reciprocal lattice point, if you see it, this vector touches this, or from here from the origin if you say this k vector touches it. Okay. Suppose I have a beam with a particular energy which is not equal to lambda, it is some other value. Then what it should be done is that vector, if it has to touch here, the angle which it satisfies with the sample surface will be different, or it essentially means that for a specific value of k, there is a particular value of theta at which only the Bragg diffraction will take place. You understand? That is what essentially means. Okay. In reciprocal space, if you try to look at it, okay, with respect to this vector, a plane which is perpendicular to the half position, okay, is the one which this scattered vector has to touch only, and that happens for some particular value of the angle. Okay. So, whatever be the vector which we have, okay, it does not matter unless this condition is satisfied, we will not get a Bragg diffraction. Or to satisfy the Bragg diffraction, if the beam energy is fixed, either you rotate the beam so that with respect to a sample surface the angle theta is satisfied, so that the vector the scattered vector touches the Bragg plane. So, this plane is called as a Bragg plane. Okay. So, this we have drawn with respect to origin for one vector, correct? So, this is another way of looking at the diffraction.
So, the Bragg plane will be only like where else will be the Bragg plane?
Now, you consider as a two-dimensional lattice. I can have a reciprocal lattice point somewhere here, I will have a Bragg plane. Okay. Now, that is precisely what it is being done. Now, this is a lattice with respect to from the origin, I can take all the reciprocal lattice vectors, okay, draw the plane which is perpendicular to it, that is the Bragg plane, correct. All the scattering vectors to satisfy the Bragg condition has to touch this Bragg plane. Okay. So, this defines an area, correct. Okay. So, this boundary, this is called as the Brillouin zone boundary. Okay. All the once a wavelength is fixed of the radiation, okay, when we have a reciprocal lattice which is there, okay, then we know these are all the k vectors, okay, which will be touching the Brillouin zone boundary. Only those vectors will give rise to a diffraction peak. Okay. So, if the wavelength is fixed, we know what the value of k for the incident beam is going to be. So, that will tell you how the beam should be oriented so that we get a diffraction peak. Okay. That becomes clear from it. So, this is nothing but in reciprocal space as in or in Fourier space, okay, equivalent to a unit cell like Wigner-Seitz cell, exactly the same way it is being constructed, right. How is Wigner-Seitz cell is constructed? Wigner-Seitz cell is a primitive cell, okay, in real lattice which exhibits all the symmetry of the lattice. Similarly, in reciprocal lattice, Brillouin zone, this is called as the first Brillouin zone, then you have second, third, like that. This is for a two-dimensional lattice we can construct it. We can construct it for three-dimensional lattice also. So, this concept of Brillouin zone also can be used to explain diffraction, right. A wall sphere construction can be used to explain a constant diffraction. So, there are so many ways we can look at the diffraction. That is what I wanted to tell you. Okay. That is the message which I wanted to convey to you. You have any doubt on whatever has been told so far? Brillouin zone. See, this is the incident beam direction, k vector, the direction the beam is coming. This is the scattered vector, correct? This is the point from which it is getting scattered, correct? And this difference between k dash minus k has to be equal to g. That is a condition for Bragg condition. Good. So, this is nothing but from here to here is a essentially a reciprocal lattice vector. So, that is precisely what I had shown here also. The same vectors can be shown like this also. Okay. And the plane, if you consider this surface here, this surface is nothing but we call that this is the plane which is diffracting. Na? What does this plane, is it with respect to reciprocal? This plane is perpendicular to that. This is exactly what we call in a Bragg law. Na? If you look at it as a Bragg law, okay, we have some diffraction planes. The reciprocal lattice vector is always normal to the diffraction plane, correct? And the distance at which the Bragg plane comes in reciprocal space is at midway between the reciprocal lattice vector. Okay.
So, the Bragg plane corresponds to the lattice plane.
It is similar to a lattice plane, because when we draw the this one, we can draw it in any way. Okay.
So, then how do you, where is the k dot half g square?
No, this is, if this is g, this will be half g, correct? This will be half g. Okay. K dot half g, if you take it, that is k dash sin theta, cos theta. Okay. This sin theta, the projection which is what we have to take it with respect to this, okay, that has to be half g squared, it will be turning out to be, correct. So, this vector has to always touch this plane, that is the scattering vector. If it touches this plane only, this condition will be satisfied, because this is the condition for Bragg law. That is essentially what we are looking at it. So, like this is with respect to from the origin one g vector we have considered, with all the vectors which are reciprocal lattice which are close by reciprocal lattice vectors, we can draw planes perpendicular to this, okay, and generate a cell, okay, and this cell is called as the Brillouin zone, first Brillouin zone. Okay. Similarly, second Brillouin zone, third Brillouin zone, like that it comes. Okay. Essentially, this concept of eval sphere is the one, and eval sphere construction is the one which is used to develop different type of X-ray diffractometers. Okay. We will just have a look at it. You assume that a monochromatic beam is falling on the sample in some particular direction in the crystal. Okay. With respect, we have defined that k dash vector. Okay. Then we are drawing a eval sphere construction. Okay. When you have drawn this eval sphere construction, what all the reciprocal lattice parts which touch the eval sphere, okay, for the particular direction in which the beam is entering, will give rise to the diffraction parts. Okay. When wavelength of the radiation and the lattice parameter of the sample is close by, then only very few spots will satisfy Bragg condition. In some condition, none of the spots be satisfying the Bragg condition. That can also happen for some direction of the beam. Okay. So, we have to essentially, why we are rotating the beam is to make it satisfy the Bragg condition. This is precisely what is being done. Okay. So, in such a case, what is going to happen is that in this type of if we make a diffractometer like this, okay, hardly very few spots will come. Okay. If you want more spots, what we have to do it is, this is one technique called as a Leavitt diffractometer. This is the one which is used to find out, okay, orientation of single crystals, especially if the sample is a single crystal, we will not be getting many spots. Okay. What do? We change the wavelength of the radiation. It is a continuous X-ray if we take it. Okay, wavelength varies from one value to another, but it is coming in the same direction. If the continuous X-ray falls on this, what is essentially going with respect to a reciprocal lattice point, if you consider, the wave vector is going to be in the same direction, but the magnitude is going to be different. So, with this as the point in this particular direction, if you draw, we will be finding out the centers at different points. You draw the Yavol spheres corresponding to it. Okay. Now, what is going to happen is that if you look at it, between this circle and this circle, okay, these are two extreme values of lambda. Okay. You have so many circles are there. So, one or the other is going to satisfy touch the reciprocal lattice. So, now we have more spots are going to, especially in a single crystal when you wanted to find out the orientation. Okay. Otherwise, if you put a beam on a particular direction, no diffraction spots will come. So, if you put a continuous radiation where the wavelength is being varied continuously, then we will be getting a lot of diffraction spots, because the Yavol sphere, when you look at it, okay, Yavol sphere is continuously, radius is changing, because of it many reciprocal lattice spots will be touching. This is the basic principle on which this Lovell diffractometer is constructed. You might have heard of this oscillation method for single crystals. What is normally being done is that you take the single crystal, X-ray beam is coming, then around an axis which is perpendicular, the single crystal will be rotated around it, so that more spots come. Okay. When we do a rotation like this, when the wavelength of the radiation is kept the same, monochromatic radiation, okay, once the sample is fixed, we know the Yavol sphere is already, and now what we are trying to do is around this axis, okay, we are only trying to rotate the Yavol sphere. So, when we rotate the Yavol sphere, I have just shown the two extremities. Okay. Now, if you see is that all the spots which are lying on this light green color between these two where they are intersecting, all of them will be appearing on the diffraction pattern. Okay. This is precisely what it happens for an oscillating crystal method. This type of crystal diffractometers are there for finding out lattice parameters and symmetry of these single crystals.
Both the methods in the same pattern we get.
Which one?
Same pattern we are changing the rather than oscillating.
No, here what we are doing, it is wavelength is not being changed. Monochromatic wavelength is there, only the sample is being rotated. When we rotate the sample, what are we essentially rotating? We are rotating the Yavol sphere in such a way that for some particular angle, the reciprocal lattice spots will be touching the Yavol sphere, right. So, we are making, yeah, so more spots are touching, so we get more diffraction spots, correct. So, that is what is being done. The another method of it is that the whole, that sample itself can be done, it is around 360 degree around an axis, you can rotate it. That even if the sample is a single crystal, by rotating it, that sample continuously, we will be able to get, okay, at different positions, okay, at the different directions of the beam, we will be able to get diffraction spots. It is nothing but what is being done here is that, okay, these are all, the red line shows, these are all the with respect to origin, which are the vectors which has to be taken. With respect to this vector, now I have constructed a reciprocal lattice, constructed an Yavol sphere like this, all these Yavol spheres have been constructed. Now you see that around this red circle which is there, all the reciprocal lattice points which are going to be there in this reciprocal, all of them will give rise to a diffraction spot. This is a geometric construction which shows that what all reciprocal spots which are going to appear in the diffraction spot. Okay. Because the beam direction, when we rotate the sample, keeping like this, the beam direction is going to change with respect to a sample, correct? This is the rotating crystal method. Okay. The same method and another form of it is what we call it as the de Besserer powder pattern. In powder pattern, what we do? We take the sample and powder it and put it. So, that means that the beam is remaining that same, but the powder is taking all orientations. It is exactly equivalent to it. You understand that? Okay. So, this is also based on the same principle of the Eval sphere. So, that is exactly what is being shown here. Okay. But in a single crystal, the rotation method, around a particular direction the single crystal is being rotated. Now here the crystal itself is as if the single crystal can be rotated not only around this, or various orientations of the axis we can rotate it. That is what is going to happen in the case of a powder diffraction. In that case what will happen is that instead of getting all the reciprocal lattice parts, so around any direction, if a point here is satisfying it, around this direction if I rotate it, all other, because there will be some orientation of the crystal will be there which satisfies it. So, you will be getting a continuous ring pattern. That is why if you look at the Debye-Scherrer this diffractometer, essentially you might have noticed it that there will be a center spot, you will be getting, this is on the film, you will be getting a continuous lines like this which will be coming. Okay. So, that is also based on the same Eval sphere construction. So, the equipments are constructed in such a way that more reciprocal lattice parts appear there, so that the analysis is simple. Okay. Most of these things, if you see the solid state physics book by Ashcroft and Mermin, there also he had explained, I had taken it from there only. He had explained very nicely how using this Eval sphere, the Eval sphere construction forms the basis of various diffractometers which we use for X-ray analysis. Because this is very, yes, Ashcroft and Mermin. Actually in the first class when I had mentioned that I had given all these books name is there, solid state physics. Okay. Now, why I wanted you to know is that diffraction is a general one. Okay. Suppose you are working with a single crystal, example that you wanted to study deformation behavior in a material, crystalline material. Okay. How the deformation behavior depends upon orientation of the sample. Then you have to take only a single crystal. Then the single crystal has to be, the loading direction has to be fixed in the single crystal. To do that, first thing which you require is that the crystal which you have got, what is the loading axis you have to find out. Na? So, with respect to external shape, first thing which one should do is to find out how surface normals, what are the directions that you have to find out. Na? That can be done using Levet diffraction. This Levet diffraction could be used to find out even on an optical microscope. Okay. On single crystals you can mark all the directions of planes and everything. It is very powerful. So, just do not think that it is, but depending upon this, when you do research you find that for some particular result which you are looking for, you have to use a particular type of a diffraction setup. That is why I am telling you about it. Okay. Like why do we go for a powder crystal diffraction? Tell me. What is an advantage of powder crystal diffraction?
If you are doing around single crystal, you are fixing an axis.
Yeah. Actually, the information about the single crystal, that is true. Even from a powder if you take it, okay, and if it is oriented in all directions, the crystal structure determination could be done from even a powder sample. It is like a powder sample is nothing but a polycrystalline material, but with all the random direction, still we can get all the point group symmetry space, everything could be determined from that pattern itself. Okay. That has that advantage.
Then why do we have like single crystals?
Eh?
Then why do you use single crystals? If, like, what else can we get only from single crystal and not polycrystal?
All material you can't powder it and use it, correct? Different setup for a different purpose when you wanted to use. Eh? No, one is an isotropic property you want it, okay. Otherwise, suppose you have made a sample, because when you do in a powder form, it is a non-destructive technique. correct? You can't go back to the original sample, you can't bring back, right? For many applications we do require single crystals of finite size, okay? But then we require information about the single crystal as we have grown, okay? Then this is one technique which is very powerful, okay? Like in some samples we can make them into powders, but not all. Many of them are grown into a powder form, okay? Many of the metallic samples, when you try to do anything, you get deformed the sample. It is not that easy to get powder crystals, powder. Okay. Generally for metallic samples what you do it is you take some turnings, okay, and then what you do it is try to, because when you make a turning that will be heavily deformed, then you have to anneal it, okay, there are a lot of changes will happen. Okay. It is not that, that is in a powder form when it is available you can use it in many of the ceramic samples, but it is not that you can replace it with that. There are many cases it is not possible.
Why do you have those lines in that?
Which one? Yeah, this is a, which one? These lines.
Those circles, yeah.
That is what I said, that this circle is essentially is that if I take any one particular direction, okay, one orientation sample is there, I get a peak, okay. If all other orientations will be there around this, if I rotate it, there will be many peaks will be there. A simple example which I will tell you. Suppose I take a cube like this, okay. This is the direction in which the beam is coming, okay. You assume that these planes are the ones which give rise to diffraction. So, which is the direction in which the diffraction spot will come, which will be perpendicular to this, correct? In this direction is where the diffraction spot will come, maybe with respect to center somewhere it is coming, okay. With respect to this direction, if I rotate the sample, what will happen? Because if it is a powder, it can have so many orientation, then what it will happen to this spot? So, you get in a diffraction spot, you get a circle like this, you will be getting it, okay. This is exactly on a 3 dimension you consider it now. It is essentially a spherical surface on which it will be cutting, and this is what an arc of the circle is what we are going to get it there, okay. So, this with respect to a thin strip, if you put a film around that sample, then you will be getting arcs like this, okay. Okay. So far what we have considered, what are the things we have considered today? One, looking at the basic condition delta k equals G, okay, the evolved sphere construction, right, and then Brillouin zone concept, okay, how this evolved sphere construction gives rise to diffraction pattern and how the diffraction patterns appear on the screen, that we have looked at it, okay. In that, only thing which we have not considered, that expression which we have written, d into d equals lambda into L. This is for the condition when theta, Bragg angle theta is very small, okay. But when theta is large for X-ray diffraction, okay, you try to find out what will be the relationship, because what we do essentially is the sample is kept at some distance, or we are trying to the radius of the like here the radius of the circle over which the detector is being moved here. So then you can find out what is the angle at which, what is the distance at which you have to move it to get the diffraction spots, you can find out that relationship, okay. I will stop here.